In this video, we're going to talk about how to write functions as certain power series. And so our starting point here is going to be the geometric series. And just remember what we already know. I'm going to write this a little bit differently than I normally do. But if we have something like 1 over 1 minus t, or 1 over 1 minus x, or 1 over 1 minus whatever, you can represent this as the sum of t to the n as n goes from 0 to infinity. And so that's the standard formula for the geometric series that's valid if and only if the absolute value of t is less than 1. Okay, so that's old news. In fact, that's news from 11.2. The reason that I'm bringing this up, though, is that we're going to be able to use this and exploit this formula for the geometric series to get representations of functions as power series for all sorts of functions. So, for example, if we had x cubed over 1 minus x squared, and I want to write that as a power series, what we could do is we could take the x cubed out. We'll see what to do with that in a second. And this is 1 over 1 minus x squared. And now our x squared is just our t. So this is going to be x cubed times the sum of x squared to the n as n goes from 0 to infinity. And this formula is going to be valid if and only if the absolute value of x squared is less than 1, which is the same as saying the absolute value of x squared is less than 1, which is saying that the absolute value of x is less than 1. Okay, so these are all equivalent statements. And I can take this series here, and we can actually write this as x cubed times the sum of x to the 2n as n goes from 0 to infinity. And you notice that x cubed is a constant with respect to the index of the sum n. There's no n's in this x cubed term, and therefore I can move it into the series with no problem. So this is the sum of x to the 2n plus 3 as n goes from 0 to infinity. And that's our power series representation. That's x cubed over 1 minus x squared. And that's valid as long as the absolute value of x is less than 1. Okay, so we're going to basically take that trick and use it over and over and over and over in this section. And so we could do things that are, for example, if we had x to the 7th over 4 plus x cubed. Okay, what we could do with this is we could take the x to the 7th out so that we have 1 over something. Let me actually just do it this way. Let's say we have x to the 7th over, I'm making this one step too complicated, but let's say I have x to the 7th over 1 plus x cubed. And we could still bring up the x to the 7th term, but it's better to think of 1 plus x cubed as 1 minus a negative x cubed. And now everything is fine. So now this is x to the 7th times the sum of negative x cubed to the n as n goes from 0 to infinity. This is going to be valid if and only if the absolute value of negative x cubed is less than 1, which happens to be when the absolute value of x is less than 1. Okay, basically the same reasoning as before with the, so is before here, with the extra step that the absolute value kills that negative in front of the x cubed. Okay, so negative x cubed, if we take the absolute value, the negative drops. Okay, otherwise it's the same argument as above. And if we simplify this, this is going to end up being x to the 7th times the sum as n goes from 0 to infinity of negative 1 to the n times x to the 3n. And so that's going to be the series from n to infinity of negative 1 to the n x to the 3n plus 7. Okay, that's a power series representation for this function. And all we really needed was the formula for geometric series. And so one more kind of complication that we can make here, if we were to have, say, x cubed over whatever, 4 plus x squared, okay, something like that. We could bring out the x cubed like we would. And I'm also going to bring out the 4. And so we bring out the x cubed so that we got a 1 up top. I'm going to factor a 4 out of the denominator so that we got a 1 here, because we know how to deal with 1 over 1 minus t. And then what we're left with after we factor out a 4 here is x squared over 4. Okay, and then we can think of that as minus a negative x squared over 4. And this is going to end up being x cubed over 4 times the sum of negative x squared over 4 to the n as n goes from 0 to infinity. And again, we can simplify that a little bit. This is going to be, we're going to have negative 1 to the n. We're going to have an x to the 2n, which times this x cubed is going to be x to the 2n plus 3. And then we're also going to have a 4 to the n times 1/4. So it's going to be divided by 4 to the n plus 1. I think that's about as complicated as these get. And so this is going to be valid whenever the absolute value of x is less than 1. Okay, so that's going to be our power series representation of this function. So that's the first thing. Okay, so that's kind of going from, is going a little bit backwards. Before I'll give you the series and ask for the function. Here I'm giving you the function, writing it as a series. Okay, so that's the first step in this section. The next step is to talk about when is it okay to differentiate and integrate power series. And it turns out we have a theorem for that. If we have a power series f, so let's say this is just a generic power series, c sub n x minus a to the n, as n goes from 0 to infinity. And if this has radius of convergence r, so if that has radius of convergence r, here I'm assuming r is not 0, then it turns out that the derivative of f is going to be given by the derivative of the terms. In other words, the derivative is going to work basically like you would differentiate a polynomial. What would happen is you're going to have the constants stay, the power comes down in front, so that n goes in front. So it's going to be n x minus a to the n minus 1. And here you can start the sum at 1 if you want, because when you write out this power series, think about what this is. When you write out this power series, this is C0 plus C1 x minus a, C2 x minus a squared, and so on. And notice that the 0th term is a constant, and that vanishes when you differentiate. So there is no n equals 0 term. If you include the n equals 0 term, you don't have a problem anyway. So if you want to write the derivative starting at 0, that's also fine because you have an n here. So when n is 0, this quantity is 0 anyways. At any rate, this is the derivative. And this is going to be valid if the absolute value of x minus a is less than r. In other words, this is valid for all x values inside the radius of convergence. Okay, so this is valid not at the endpoints necessarily, although sometimes it is, but it's it's always valid inside the interval of convergence. Okay, so that's the first part. And then the second part is that inside the radius of convergence, the integral is also going to behave the way that you think. The integral of f of x is going to be the sum of, well, we just integrate term by term. So we're going to take our x minus a to the n, we're going to add 1 to the exponent, divide by the new exponent. And we get c sub n over n plus 1, x minus a to the n. And again, just think about how this series is going to look. When you integrate it, you're going to get c0x plus c1 x squared over 2 plus c2 x minus a cubed over 3, and so on. And so you get c sub n over n plus 1, x minus a to the n plus 1. And this is also valid if x satisfies the inequality x minus a is less than r. Again, possibly valid on the endpoints, but it's always valid inside the interval of convergence. Okay, and so it turns out that we can differentiate and integrate a power series term by term if we're inside the radius of convergence. Now, this is going to be very useful for us for a few reasons. One is that this is going to allow us to actually evaluate some series we couldn't evaluate before. So for example, if we had the function, just start with 1 over 1 minus x as our geometric series. This is x to the n, as n goes from 0 to infinity. And that's old news. This is if the absolute value of x is less than 1, of course. However, if we differentiate, think about how would we differentiate 1 over 1 minus x squared? It turns out that 1 over 1 minus x squared, if we differentiate, we're going to have 1 minus x to the negative 1. So that'll be negative 1 minus x to the negative 2 times the derivative of the inside, which is a plus. So this works out to 1 over 1 minus x squared, quantity squared. But also we differentiate the power series. And so here our series is going to become x to the n differentiates to n x to the n minus 1. Okay, and so this, if you want to think about it as x0, so it's, let me write it a little better. This is x to the 0. So it's 1 plus x to the first plus x squared plus x cubed. And when you differentiate, you should get the 1 goes away, x differentiates to 1, and that's the n equals 1 term. The derivative of x squared is going to be 2x, 3x squared, 4x cubed, and so on. Okay, and so that's how this is going to work. So that's the derivative. Now, the reason why I say that that is useful is the following. So let's say I want to evaluate. So let's say I want to evaluate the sum of 1 over n times 1/2 to the n. Okay, or I might have probably, maybe I should have written it as 1 over n times 2 to the n. Okay, so as n goes from 1 to infinity, the series, we're going to get 1 over 2 plus 1 over 2 times 2 squared, 1 over 3 times 2 cubed, and so on. And so that's not a geometric series. But what we can do is a little trick here. So if I want to evaluate this, what I can do is I can let g of x or f of x or whatever, basically what I can do is I can use, I don't need to do this generically because I've already done it here, but I can use this series. And notice that this is close to what we had, and I have an n here. I have a mistake, and I want an n up top. I don't know why I put it down below. I want this n up top, so n over 2 to the n. So I want 1 over 2 plus 2 over 2 squared, 3 over 2 cubed, 4 over 2 to the 4th, and so on. Okay, that's really the thing I want to evaluate. And so we know that if we have n times x to the n minus 1, if that's our series, then that's going to evaluate to 1 over 1 minus x squared. And so what we can do is we can use this, and here I really want to deal with n times x to the n. And the way that we can do that is just multiply both sides by x. So we know that 1 over the quantity 1 minus x squared is equal to the sum n x to the n minus 1, starting at 1. And therefore, if I multiply both sides by x, then x over 1 minus x squared is going to be equal to, well, the series is also going to be multiplied by x. And that'll just be n times x to the n. Okay? And so this is exactly what we have. We have n times x to the n, where x is 1/2. So this tells us that the series n times 1/2 to the n, as n goes from 0 to infinity, is going to be 1/2 over 1 minus 1/2 squared. So I'm just looking through and replacing all of our x's with halves, and that's what we get. So this is going to be 1/2 divided by, let's see, 1 minus 1/2 is 1/2. 1/2 squared is 1/4. And so it turns out that this is going to be 4 over 2, or 2. Okay, so that's how that series evaluates. This turns out to be 2. Okay, so that's another nice trick that we can do with these. It turns out you can always differentiate or integrate inside the radius of convergence of a power series. One last application of this, and I want to do possibly 2 examples, but just one last application is that there's now some functions that are not too far from geometric series that we can write as power series. So for example, let's start with the natural log of 1 plus x. And I want to write this. So I want to write this as a power series. Okay, and there's various ways to do this, but I think the easiest way to do this is if we take f of x, which is the natural log of 1 plus x, notice that the derivative of f, notice that f prime is 1 over 1 plus x. And that's very close to a geometric series. And it turns out that we're gonna really exploit that. So f of x is actually going to be, if I want to think about it this way, I can think about it as the integral of the derivative. So natural log of 1 plus x is the integral of the derivative of the natural log of 1 plus x, because integrating the derivative undoes both of those operations. They're inverses based on the fundamental theorem of calculus. And what this means, is that if I can evaluate this integral, then and write it as a series, then we have a series representation for the natural log of 1 plus x. So for starters, what we have is 1 over 1 plus x, we can write as the sum of negative x to the n, as n goes from 0 to infinity. Okay, and so this is valid if x is between -1 and 1, as always. And what we can do then is simplify this a little bit. And we have the integral of the sum as n goes from 0 to infinity of -1 to the n, x to the n dx. And notice that the integral is with respect to x. The sum is with respect to n. And so it turns out, and we have to kind of work pretty hard to see why this is true, but it turns out that I can exchange the integral and the sum. And so this is, yeah, I'm just going to completely take this for granted for now, but it turns out in this case, it's fine. You can interchange the sum and the integral, and we get the integral of, let's see, -1 to the n. -1 to the n is a constant with respect to x, so I'm going to bring that out. Then we have x to the n dx. And it turns out when we integrate this, we're going to have the sum as n goes from 0 to infinity of -1 to the n times, let's see, 1 over n plus 1, x to the n plus 1. And we're also going to have a term in there plus c, which is going to be a little bit annoying. But it turns out that this constant that we're going to get from integrating is going to turn out to be 0, the way that I've written it here. And the reason why it has to be 0 is that this is not representative of some generic function. This is representative of the function, the natural log of 1 plus x. And so if I plug in a value, say x equals 0, which is certainly in the range of x's that we have, if I look at the natural log of 1 plus 0, on the one hand, I get 0 because that's the natural log of 1. On the other hand, we get this sum. Excuse me, we get this sum. So on the other hand, we get the sum of 0 to the n plus 1 plus c. Now, the only time when you could possibly get a value from this sum is when you were to have 0 to the 0. But here we don't have that. The smallest power that we have is to the first. So that we don't have a 0 to the 0. We have 0 to the first, 0 squared, 0 cubed. All of those are 0. So all of those terms in that sum are 0. And therefore our constant of integration has to be 0. So c is 0. And so what we just showed, just in summary, is that the natural log of 1 plus x can be written as the series from n equals 0 to infinity of -1 to the n times 1 over n plus 1, x to the n plus 1. And this is valid if and only if the absolute value of x is less than 1. Okay, and so here, that's how we can write the natural log as a power series. Okay, so the natural log of 1 plus x has this power series representation. This is going to be very useful for us. Okay, and then just last example for this section, we can do the same trick, except I'm going to look at the function arctangent of x. And this is a very similar trick. This is going to be, I think the best way to think about this is the integral of the derivative. And then we'll have to deal with the plus c again. Okay, so the integral of 1 over 1 plus x squared. And let's see what's going to happen here. We're going to have, let's see, 1 over 1 plus x squared, we can write as a geometric series. So this is the integral of negative x squared to the n, as n goes from 0 to infinity. We're integrating with respect to x. And then we can do the same tricks as before. We can write this as the sum of negative 1 to the n times x to the 2n, as n goes from 0 to infinity, dx. And then this is going to be, we can switch the role of the sum and the integral. So we can put the sum outside and the integral inside. The negative 1 to the n stays outside. We're integrating x to the 2n dx. And that's going to end up being negative 1 to the n. So the sum of negative 1 to the n times 1 over 2n plus 1, x to the 2n plus 1. And then we would have a plus c again, but the same argument, because arctan of 0 is 0, and because this quantity is 0 when we plug in 0, that means the constant has to be 0 too. And therefore, what we have is that the arctangent of x is equal to the integral of 1 over 1 plus x squared. I'm sorry. I don't mean to copy that part. I meant to copy the sum from n equals 0 to infinity, negative 1 to the n of 1 over 2n plus 1, x to the 2n plus 1. It turns out that's the right way to write arctangent as a power series. And this is valid, I forgot to say, if the absolute value of negative x squared is less than 1, or a little more simply, if the absolute value of x is less than 1. Okay, and so that's basically how we can turn those functions into power series. And those functions are special because their derivatives happen to look a lot like the functions that we were working with in geometric series. Okay, so that's that for now. I'm going to come back in the next video and talk about these last two examples in a little bit more detail.